So, quick review. So this is the symbol. This is the atomic number, which is just the number of protons. And this is the mass number, which is equal to number of protons plus number of neutrons. We have some special cases. Zero, zero, gamma. This is a gamma ray. EM wave, electromagnetic wave. We have 0, 1 with an N. This is a neutron. The only two that have a 0 on bottom left. We get a -1 and a 0. E. This is a electron. This is technically a high energy electron. And a 10E positron, which is antimatter or positively charged electron. So these are the only 4 special cases. The rest are going to be standard elements. If you have a 0 and some number other than 1 up here, you would rewrite it. So if you have a 0 on bottom left and a 0 on top left, it's gamma. If you have a 0 on bottom left and a number greater than 1, then it's multiple neutrons. And you would write it. So, for example, if you wind up with a 0 and a 3, and you don't know what the symbol is, note that this doesn't exist. Instead, you would write it as 3 neutrons, like this. 3 neutrons. So if you wind up with a 3 and a 0, you know that since it has a mass, it can't be gamma. That means it must be neutrons, and since the top number is 3, it just indicates that you have 3 neutrons. Yes, this is also beta plus, and this is technically beta. So this will be beta plus. This is just beta. Everyone good? So, how are all the atoms larger than hydrogen made? So they're made via fusion inside of a star. This is more generic. There are technically some of them radioactively decay into different elements. Some of them were made during the supernova blast when a star explodes. But for most of all, this statement will consider true. A nuclear bomb is what? Uses what? Uses fission, i.e. splitting the atom. So that binding energy is huge in respect to the atom. And how many atoms are in a mole? 6.022 times 10 to the 23rd per mole, and that's only like a few grams. Or technically, it could be up to a few hundred grams. So, for example, if we look at uranium, well, we don't even need to look. Let's look at uranium 235, which is the isotope. The isotope used in most nuclear bombs. It has 235 grams per 1 mole. That means if you had 235 grams of uranium, 1 mole is 6.022 times 10 to the 23 atoms. And if we were to split that number of atoms, and we're taking and converting the binding energy of each atom and release it, that's a really big number. So only about 2 to 3% actually get split, or maybe it's only a half. So that was actually my point. Is they realized back Einstein was helping, and a lot of few other people were working on this, and they came up with this idea that if we could harness that binding energy and release it, we could get an unimaginable amount of energy. And they came to the conclusion it's impossible. There is no possible way we can efficiently split the atom because in order to get two positive charges, so the nucleus of the atom is positively charged, and the nucleus of another atom is positively charged, in order to force them to come to hit each other, requires more energy than would be released. So they came up and were like, this is impossible. Until James Chadwick made a discovery. What did James Chadwick discover? A neutral particle. He discovered a neutral particle that would not be repelled by the positively charged nucleus. So instead of taking two positively charged nucleus and smashing them into each other, you instead take a single neutron, which would not be repelled, and make it hit a large nucleus. This would cause the nucleus to break apart. So the moment the neutron was discovered, atomic bombs became possible. And if this were to produce two or three more neutrons, these neutrons could go on and hit more atomic nuclei and split them apart. And if each one of these were to go and produce three more neutrons and hit more atoms, and produce even more neutrons that will go and hit. So this releases a few more neutrons, which goes and hits another atom, which breaks apart and releases more neutrons, which then goes on and hits another atom, which breaks apart. You can get something known as a chain reaction. Yes. But this is random. Sometimes splitting it won't produce any neutrons. Sometimes it will produce one neutron. Sometimes it'll produce two. Sometimes it'll produce three. Again, you're taking and randomly breaking this apart. And what's left over is going to, on average, uranium-235 releases 2.7 neutrons. So I believe it's 2.7. It might be 1.7. So I think if you're over 2, or if you're over 1 on average, then you can get a chain reaction. I think it has to be like 1.5. 2 is statistically would make it continue reacting. But you're also generating heat. That heat is and light is going to push these atoms farther and farther apart. It's blowing up. And anything with mass can't go the speed of light. But light can go the speed of light. The light pressure pushing will push these atoms apart. In order to have a nuclear bomb, you have to have something known as critical mass. Critical mass is the minimum amount of fissile material needed to maintain a nuclear chain reaction. So, because this is random, sometimes this chain will eventually stop if you start producing 0 neutrons. Or if the energy gets too big, you start pushing away the other atoms faster than the neutrons can physically keep up. So what happens is you have two subcritical. So they have a cone shape, and they have something that will fit directly in it, a bullet. And usually they pack high explosive on one side, which will accelerate this here. And because of the shape of the uranium components, this is going to hit with increased surface area. And this is a hollowed out sphere kind of, and this is the half a sphere. And when they collide together at high enough speeds, you will force some of them to break apart just through impact. They're also constantly decaying anyway, but if you do this at high enough speeds, you can get a bunch of uranium at the same time, reacting with some uranium over here, neutrons flying out, and you can get the reaction started. That's a nuclear bomb. Yes. So, nuclear bomb time. It's on the order of nanoseconds. So this was captured 1 millisecond, or less than a millisecond after it exploded. These trailing things are where cables were, so it's suspended by cables up here. Some of the heat flows along the cable, so this is faster than you can blink. Obviously, it's an explosion. What was the time? So, to give you an idea of how much energy, the nuclear bomb is about 100 times brighter or more energy than the surface of the sun. So the surface of the fireball is 20,000 Kelvin, over 20,000 Kelvin, which is less than the temperature of the sun. The outer surface of the sun. So it's a lot of energy. Um, so nuclear reactors, what type of energy do they use? This would also be fission. So atoms naturally decay, radioactive materials naturally decay. So if you have a reflector and can reflect some of the neutrons back, or have a emission source, you can control this rate. What they do is basically they get subcritical material, so it's just on the right point where it could go nuclear. Um, and what they do is they have like usually carbon. Carbon is a good neutron collector. Carbon likes to absorb neutrons. And you take this nuclear material and you shove this carbon rods into it. So you have nuclear rods and then you have these control rods. As long as the control rods are in between the nuclear material, they'll start absorbing a lot of the neutrons. If you raise up the control rods, some of the neutrons will start bouncing from one material to the other, and they'll start reacting more, and they'll start giving off more neutrons. There's a little chain reaction, and this starts heating up the water. If you didn't know this, all of electricity in everywhere except for solar and wind all work on the same principle. We heat up water, water turns to steam, steam pushes turbine, turbine turns a generator, and that generates electricity. Nuclear plants, coal plants, hydroelectric power plants, they all work on basically the same principle. I guess hydroelectric has a dam where the water is just falling over the turbine, but it all comes back to water or steam flowing over a turbine. A lot of solar plants are all they what they do is they have mirrors. They have a long tube of water. The mirrors reflect sun into the tube of water. It turns the water into steam. Steam gets pushed out, forcing a turbine to spin, and we create electricity. That's usually how we all produce electricity is through this effect. Y'all know why this is blue? Shrink off radiation. Light moving, our electrons going faster than the speed of light. Light is slower in water than it is in air, and because light is slower in water, electrons could theoretically move faster than the slower light. In a vacuum, the fastest speed in the universe is the speed of light. In water or glass and other materials, light travels slower through it. But the electrons have a high enough energy they can outrun the relatively slow moving light, and this produces solar booms, photonic booms. Basically, electrons going faster than the speed of light, because the speed of light in water is slower. Let's say the one thing. When balancing equations, So when balancing equations, the top numbers on both sides of the equation must equal each other. Likewise for the bottom numbers. So it's just what we've been doing. We have 4,2HE, and we have 2,1H plus whatever. We know that this has to be a 2 because 2 plus 2 equals 4. This has to be a 1 because 1 plus 1 equals 2. These have to balance each other on both sides of the arrow. And 1, 2 corresponds to hydrogen. Any questions?